Hello everyone, my name is Chandrail Chakraborty from Trinity College, Hartford. My apologies for not being able to be present in person. In this presentation, we'll discuss MemFlex, a hybrid memory system designed to address the challenges of cost and scalability in modern data centers. We will explore the limitations of traditional DRAM-based memory systems and how MemFlex can leverage non-volatile memories to offer a more cost-effective and efficient solution. So the world is experiencing an exponential growth in data, and data centers are struggling to keep up with the demand for storage, processing, and access. Traditional DRAM-based memory solutions, while being fast, are increasingly becoming expensive and faces scalability limitations. This poses a significant challenge in data centers as they strive to maintain performance while managing cost. DRAM, being the primary memory used in data centers, is facing challenges due to increased cell leakage, reduced cell reliability, and manufacturing complexities. While alternative technologies like 3D stacked RAM and emerging NVM technologies offer potential solutions, they are not yet a complete replacement for DRAM due to capacity constraints and higher cost per bit. Hybrid memory systems, which combine DRAM with non-volatile memories, offer a promising solution to this bottleneck. By leveraging the speed of DRAMs and the capacity and cost effectiveness of non-volatile memories, hybrid systems can achieve significant cost reductions while maintaining performance. This tiered architecture allows frequently accessed data elements to reside in DRAM for fast access, while less frequently used resources are stored in non-volatile memories. Efficient data placements are crucial for optimizing performance of hybrid memory systems. Traditional approaches rely on heuristic-based strategies which may not fully capture the overall system performance impact. Inefficient data placement can lead to suboptimal performance and increased cost. Therefore, a smarter data-driven approach is proposed to optimize data placement in hybrid memory systems. MemFlex introduces a novel approach for data placement by predicting the dead time of data elements. So dead time, introduced earlier, refers to the number of writes before a data element is written. By predicting the date times accurately, MemFlex can determine how long a data is likely to remain relevant and make informed decisions about its placement for optimizing performance. MemFlex utilizes long short-term memory neural networks to capture the spatial and temporal I/O accesses and predict its date times. So MemFlex is a machine learning powered solution that leverages dead times to guide placement decisions, whether to put it in memory, primary memory, or secondary memory, and so on. By training on synthetic and real-world traces, MemFlex can adapt to different workloads and optimize memory usage for specific applications. This tailored approach ensures that data is placed in most appropriate tier for maximizing performance and cost efficiency. MemFlex's machine learning model is trained on a combination of synthetic traces from Yahoo Cloud Service Benchmarking Tool and real-world traces from SNIA, Storage Network Industry Association. The trained model in MemFlex utilizes features like logical block addresses or page address, the I/O size, request, and the previous dead time of the page to predict the future dead times. The data is pre-processed to find out the dead time for each data element for training and when we filtered out read requests because they do not overwrite a data element. So our focus was only on the write requests and calculating the dead time for write operations. Thus, the model ensures that it focuses on the relevant information, so it's trained on the dead time to predict future dead times. MemFlex's LSTM model consists of two hidden layers with 500 neurons each, with an embedding layer for sparse inputs and an output layer which predicts the dead time in terms of percentile. So the output is a class between 0 and 100. The model is trained on 75% of the trace data and evaluated on the remaining 25%. Application-specific models are trained to further enhance the accuracy and tailor the system to specific workloads. MemFlex's architecture comprises of three main elements: the ML model, the memory controller, and the flash translation layer. The ML model predicts the dead time for the pages. The memory controller manages the page migration between DRAM and non-volatile memory based on the prediction, and the flash translation layer handles the NVM access. When an application requires data, MemFlex predicts the page lifetime and places the data in an appropriate tier, ensuring efficient access and optimizing performance. To evaluate MemFlex's performance, a simulator adapted from prior work was utilized. The simulator runs on the host sites and simulates various memory configurations. The evaluation metrics include latency degradation compared to a system that uses 100% DRAM memory, and performance improvement over the baseline techniques like NeMo, a cloud-based hybrid memory management tool proposed earlier, and UHMem, a metric-based utility for page migration, which these two were used as baselines. The LSTM model, from the results we see that the LSTM model consistently outperforms the random forest baseline. Random forest was used as a baseline to measure the effectiveness of LSTM model. In terms of performance improvement, MemFlex achieves an average of 19% improvement over the baseline, UHMem, and up to 90% improvement in specific scenarios. The benefits are particularly significant with higher DRAM to SSD ratios. And we also outperformed both the baselines, UHMem and NeMo. So in this section, we show the latency degradation impact. So MemFlex's performance is evaluated on real-world traces, including the TPS-H benchmark, RogsDB, which is a key value store, and traces from a virtual desktop infrastructure workload. In all of these scenarios, MemFlex demonstrates higher accuracy in dead time prediction across various workloads, ranging from 59 to 71% for real-world traces and up to 99% for synthetic workloads. MemFlex also consistently outperforms all baseline techniques in all chosen scenarios, demonstrating its effectiveness in handling diverse real-world workloads. Compared to a system with 100% DRAM, we see that MemFlex introduces minimal latency overhead. The trade-off between cost savings is considered thus acceptable according to industry standards, while latency degradation increases with more SSD usage. MemFlex mitigates the effect better compared to the baseline techniques. MemFlex, in this point, we see the advantages. So MemFlex intelligently migrates pages between DRAM and SSD based on their predicted lifetimes. Hot data, which is frequently accessed, remains in DRAM for faster access, while the colder data, which would be requested at a later time, is moved to SSD to free up DRAM capacity. The application-specific models enable MemFlex to learn and adapt to different workloads, ensuring optimal performance in various scenarios. By maximizing the use of cheaper non-volatile memory without sacrificing performance, MemFlex achieves significant cost efficiency. So, thus, MemFlex offers several advantages over existing techniques. It provides significant performance improvement, minimizes latency degradation compared to DRAM-only systems, and leverages cheaper and non-volatile memories to reduce overall cost of ownership. The adaptability of application-specific models allows MemFlex to cater to diverse workloads, and its evaluation on real-world traces demonstrates its practical value. In terms of broader impacts, MemFlex has the potential to transform data centers by significantly reducing memory costs, making large-scale data processing more affordable. It also improves application performance by intelligently managing memory and enabling faster and more efficient data access. Additionally, MemFlex contributes to sustainability by optimizing memory usage and reducing energy consumption in data centers. So, in terms of limitations, MemFlex currently requires initial offline training for each application in terms of calculating the dead time for training, which could be improved by an online training or using a transfer learning. The evaluation is primarily based on a simulator currently, and real-world deployment may introduce additional overheads that we are not aware of. Thus, further validation in production environments is needed. future work will focus on exploring multi-tiered memory systems, including various levels of memory, including cache memory, investigating energy efficiency optimizations, and integrating MemFlex with existing data center management tools.